Hello. In this video, I want to talk about solving systems of linear equations. Now, over the course of the next three videos, there are three primary methods that we use to solve linear equations: graphing, elimination, and substitution. And we won't necessarily be doing them in that order, but we're going to start with graphing today. So I'm going to go ahead and I'm going to draw out my axes. Now, we have to really think, what does it mean to solve a system of equations? To solve a system of equations is to find the solution, the coordinate pair that fits both equations, and you get if you input the x value, you get the same y value for both, okay? Now, there's a couple things that can come from out of this. So really quickly with sketches, you could get one solution. This is a very basic geometric property that two lines, if they intersect, they'll intersect at one point, okay? So you get one solution. Or what could happen is lines could be parallel. So if you get parallel lines, well, parallel lines never intersect, so that would be no solution. And then the final one is, what if you take those parallel lines and overlap them? So that would be something like this. So you get a line, and then on top of that, and I'll try to do this as carefully as possible. That's good enough. You get the same solution. So you can get one solution, or I should, say you should get the same line. So you either get one solution, zero solutions, or infinitely many solutions. Okay, let me take that off really quickly so I got more room to work. Let's go ahead and graph these. Remember, we start with the y-intercept when we're graphing in slope-intercept form. Okay, so down 4 from the origin, 1, 2, 3, 4. Okay, so I'll plot my point. And my slope is 1 over 5. So slope being 1 over 5 means we're moving up 1 and we're moving right 5. Okay, so up 1 and right 1, 2, 3, 4, 5. So right about there. And I think we got it. All right. Let's go ahead and graph the other one. I'll graph that in purple. We've got a -6 slope, so we're down 2 more from the other one, down 6 from the origin. And now our slope is -1 over 5, so this will be down 1 and right 5. Sorry, down 1. There we go. So down 1, right 5, so right about there. And there we go. Okay, so hand-drawn graphs can be a little much, and this is probably why I've never truly liked graphing as the preferred method, because if you're graphing by hand, it's going to be prone to human error, and if you get especially a decimal solution, you might not get the exact decimal. Okay, so it looks like our point, I drew out some negative x values, is approximately -5, -5. Okay. Because graphing is not the most accurate way to do this, we're going to go ahead and check our answers, which means we're going to plug in our x value of -5, and in both instances, we should get an output of -5. So here we've got y equals 1 over 5 times -5 minus 4. Well, the 5's here cancel. We're left with just -1 minus 4, and we get -5. Okay, great. So far, so good. And then down here, I will do the y is equal to -1 over 5 times -5 minus 6. And the 5's cancel and the negatives cancel, so we're just left with 1 minus 6, which gives us -5. Okay, good. We have the correct solution. Now, that is if you have two equations in slope-intercept form. And if you have them in slope-intercept form, then you can use some graphing technology like a TI-83 or Desmos to check your work. I can save that for another video. I still got 2 more examples to go, so I'm going to go through those now. All right, for our next example, we have one in slope-intercept form and one in standard form. So the slope-intercept form, same as always. We graph the y-intercept first. All right, and it's +1, so it's up 1 from the origin, and then our slope is 4. So slope is 4, and since it's a whole number, we'll have to put it over 1. This means we're moving up 4 and right 1. So up 1, 2, 3, 4, and then right 1. So there we go. There we go. Okay, great. All right, now we have standard form, which means we need to resort to using intercept math, which means I'll plug in 0 for x. 0 for x means I'm solving for the y-intercept. That cancels, and we get 2y equals 2 divided by 2. We get y equals 1. Okay, great. Looks like we have an intersection. But let's go ahead and get the x-intercept, which means I'm plugging in 0 for y. So, 0 for y, so 2 times 0 equals 2. That cancels. Negative 8x equals 2 divided by negative 8. So x should be equal to negative 1/4. Now, I suspect that's this point right here. Let's go ahead and plug this back into this equation to check to make sure that math is correct. Because if that is the point, then we're going to end up with an infinite solution set answer here. So I'm going to plug in y equals 4 times negative 1/4 plus 1. And remember, it's the x-intercept, so if this is the same line, I should get 0 as a solution. So 4's cancel, and I'm left with negative 1 plus 1, and I get 0. So these are, as I carefully trace over my previous line, the same line, which means we have infinitely, in fact, I'll just use the infinity symbol, infinitely many solutions. Okay, awesome. Let's go ahead and try one more example. This time they're both in standard form. So I'll go ahead and plot my axes. Okay. We're going to have to do intercept form for both of them. So I'll do this first one in red like I've been doing. So I'll solve for y-intercept first. Now this is a tricky thing about this sometimes, is I've noticed this happens when we drop out this 5 times 0, we also lose the negative. Don't lose the minus, it becomes a negative. And we just got to think negative y equals negative 3. That just means y equals 3. And if you don't know how to do that, just divide both sides by negative 1. So my y-intercept is 1, 2, 3. Okay, and then let's go ahead and do 5x minus 0 equals negative 3. Let's cancel that out. Let's divide by 5. And we get x equals negative 3 over 5, which is negative 0.6 as a decimal. So here's 1, and we'll go a little bit more than halfway. So this is an answer we're probably going to have to estimate, but we will check our answer at the end, assuming we don't get infinitely many solutions, again, which we probably won't. And I'll do this one in purple. So 0 plus 3y equals negative 23. So we'll divide by 3. Again, cancel that out. I'm running out of room, so I'm really shorthanding this one. So this is negative 23 over 3. Well, negative 24 over 3 would be negative 8, so this would be negative 6 2/3. So 1, 2, 3, 4, 5, 6, 7, 8, and about 2/3 of the way there. Okay, and then we get x plus 3 times 0 equals negative 23, and we get x equals negative 23. So we're really going to have to stretch this out. Let me go ahead and do a cut with a modified axis. 1. Okay, so I went ahead and graphed it and finished it. Not the greatest line in the world. Probably should use a straight edge tool or something like that, but that's okay. It'll do for now because I found my point negative 2, negative 7. That is an estimation because we're graphing by hand. Let's go ahead and check it. So I'm going to plug both of them in, and the equation should balance out. So 5 times negative 2 minus a negative 7 equals negative 3, and we should put a question mark technically because we're checking. So we get negative 10 here, and then this minus a negative here becomes plus 7, and we can see this one does indeed balance out. So we're so so good. Okay, let's go ahead and do the other one. We've got the -2. X is no coefficient other than 1, so plus 3 times -7 equals -23. We'll go ahead and put our question mark there. -2 is 3 times a -7 gives me a -21, so all my -21 equals -23. And we can see this also does indeed check out, and we are done. I hope you gained a little bit of appreciation for what it takes to graph a system of linear equations. If you'd like to see more examples like this, leave a comment in the comment section. Otherwise, like and subscribe, and I'll see you for the next video. Thanks for watching.